Welcome to the Deep Dive. Today, we're going deep into something, well, honestly, it's absolutely crucial to the internet as you know it. Automated database failover in a multi-region setup. Now, stick with us even if that sounds like heavy tech jargon, because this is really the invisible safety net beneath almost every online service you use.
It really is.
Think about a moment when a website or app didn't go down during some major event. Chances are, systems like these were hard at work, humming away in the background.
Definitely.
So our mission today is to unpack the core principles, the ideas that allow for this incredible resilience. Trust me, understanding this is not just informative, it's actually genuinely fascinating.
It is. It's pretty clever stuff.
We're looking at how these complex systems are built, and we're here to pull out the essential, maybe even surprising insights.
That's right. At its core, what we're talking about is ensuring that your applications stay up and, crucially, your data remains secure, even when really big things go wrong.
Big things like,
Oh, planned maintenance that maybe goes sideways, or, even a major weather event knocking out an entire region. Stuff like that.
wow, okay.
And the bedrock of this kind of resilience is a really well thought out architecture.
Okay, let's unpack this architecture. Our sources mention a primary-secondary hierarchy. What does that actually look like on a practical level?
Right. So imagine a single central hub, let's call it the right primary, in your main operating region.
Got it. The main hub.
This is where all the action happens, all the adding, changing, deleting of data. Now, within that same region, you'll typically have what are called synchronous replicas.
Synchronous meaning in sync.
Exactly. Think of these as immediate live shadows of the primary. And crucially, the primary waits for at least one of these synchronous replicas to confirm it has the change before it tells the application, okay, write complete.
So that keeps things consistent right there.
Yep, gives you strong data consistency right there in the primary region.
So it's like a safety deposit box with an immediate backup copy in the same vault.
Oh.
Okay. But what if the whole vault has a problem? That's where the secondary regions come in.
Exactly right. That's where your asynchronous replicas live. These are also copies of your primary data, but they're located in geographically separate regions.
Okay, different locations.
And the updates from the primary are sent to them, well, asynchronously, so with a slight delay.
A trade-off then. A bit of lag for geographical safety.
Precisely. This trade-off, a tiny bit of lag, lets you spread your data across the globe without slowing down those critical primary write operations.
Makes sense. The sources also talk about redistribution. How does that fit into making things faster or more resilient?
Right. So to ease the load on that busy primary database and, boost overall performance, you can direct read requests just looking at data, not changing it.
Right, the reading part.
Yeah, you send those requests to these read replicas, which can be in any region, primary or secondary. Now, here's a really crucial point, consistency levels. If an application reads from one of those asynchronous replicas...
The ones with the slight delay.
Yeah, there's a chance it might see data that's maybe a fraction of a second out of date compared to the primary.
So not instantly up to date.
Potentially. And the application's needs, what it's doing, will dictate how much of this staleness is acceptable. It's a balancing act, really, between speed and always having the absolute latest information everywhere, instantly.
Gotcha. Choosing the right level of up-to-the-second accuracy for different tasks. Now, the idea of data center pairing, that sounds like having a buddy system for your data centers.
That's actually a great analogy. Think of it exactly like that, like having a prearranged emergency contact and a backup plan ready to go.
Okay.
Each primary production region has a designated failover region paired with it. And this partner region already has resources, compute, storage, network capacity kind of warmed up and ready.
Pre-provisioned, yeah.
Pre-provision and ready to take over if the primary region has a major issue. It's all about that proactive planning, so you're not scrambling when, things go wrong.
Got it. So the architecture is the foundation. Very clear. Now, how does the data actually get copied from primary to all those replicas? Our sources detail different replica implementation strategies. Sounds like there's no single silver bullet here.
You're absolutely right. The choice of replication tech really hinges on the specific database you're using. They all have their own ways.
Like what? Give us some examples.
Okay, well, take PostgreSQL, a very popular one. A common approach is logical replication. You might use the primlogical extension or its built-in native logical replication feature.
Logical means.
It means it replicates based on the actual changes made to the data itself, the logical changes, rather than just the raw disk blocks.
Okay, and for other big databases, like MySQL or SQL Server.
Right. For MySQL, you might see group replication, which is pretty robust for consistency across nodes, or maybe semi-synchronous replication paired with something called global transaction identifiers, or GTID.
Word ladies.
Yeah, they're really useful. They basically give every transaction a unique ID across the whole system, which simplifies setting up replication and makes failover much, much cleaner.
Nice. SQL Server.
SQL Server often uses always-on availability groups. For cross-region stuff, you typically configure that with asynchronous commit just because of the network distances and potential delays.
It's that latency.
Yeah. MongoDB uses replica sets with something called majority write concern. That means a write has to be confirmed by most of the copies before it's considered successful.
Safety in numbers.
Pretty much. And then, of course, you have the cloud-native databases, things like Amazon's Aurora Global Database, Azure's Cosmos DB multi-region, Google's Cloud Spanner?
The ones built for the cloud.
Exactly. Many of these have multi-region capabilities built right in. They handle a lot of this replication complexity for you, sort of under the hood.
That's convenient.
It is. But what's fascinating is just seeing how each database system has evolved its own, robust way of tackling this fundamental challenge of copying data reliably.
It's almost like each one speaks a slightly different dialect of data replication.
Oh.
Okay, but across all these methods, replication lag management keeps popping up as super important. Why is keeping such a close eye on this delay so critical?
Replication lag. It's basically the time difference between a write happening on the primary and it showing up on the replicas. It's a vital sign, a really key indicator of your system's health.
Like a pulse check.
Kind of, yeah, because if this lag grows too large, especially if you're heading towards a potential failover, you face a very real risk of losing data. Or ending up with inconsistent states when the secondary tries to take over.
Ouch. Yeah, you don't want that.
Definitely not. That's why continuous monitoring of this lag is absolutely essential. You need to set alert thresholds based on your recovery point objective, or RPO.
RPO, recovery point objective. What does that mean in practice?
Think of RPO as defining your tolerance for data loss. It's the maximum amount of data measured in time that you're willing to potentially lose in a worst-case disaster scenario.
Okay, so we can afford to lose maybe the last 5 seconds of data.
Exactly. So if your RPO is, say, 5 seconds, you'd absolutely want an alert firing if your asynchronous replicas start falling, 10, 15 seconds behind, because you're outside your tolerance.
That makes perfect sense. You need to know if your backup is falling too far behind to actually be useful when you need it.
Okay.
The sources also mention something called change data capture, or CDC. How does that fit into this whole picture of keeping data in sync?
Right, CDC. It's a more, let's say, sophisticated and often more flexible approach than relying purely on the database's built-in replication.
How does it work?
Well, CDC systems, things like Debezium are a popular example, essentially listen directly to the database's transaction logs. That's the detailed history of every single change.
The database's internal journal.
Precisely. They capture these changes from the log and then stream them to other systems. And those other systems could be your secondary databases, but they could also be data warehouses, analytics platforms, anything really.
So it's more decoupled.
Exactly. It offers greater flexibility, especially in really complex environments or when you need to integrate database changes with lots of different parts of your data infrastructure. It's like having a dedicated scribe meticulously recording every single update and then relaying it wherever it needs to go in near real time.
Interesting. Okay, so we've got our data being replicated across regions, maybe using built-in features, maybe using CDC. But how do we actually know when the primary database is having serious trouble and we actually need to make the switch?
That's where comprehensive health monitoring comes in, right? Like an early warning system. Precisely. Reliable automated failover, the automated part, absolutely depends on accurately and quickly detecting problems with the primary database. And it's not just a simple check like, is it online or offline? Ping it. No.
Much more to it than that.
Oh, yeah. It's about looking at the health from multiple angles, multiple dimensions.
Okay, what kind of angles are we talking about? What are the key vital signs we need to watch?
Well, first, at the database level itself, you'd be looking at things like query execution time. Are simple requests suddenly taking way longer than usual?
Downs, yeah.
Connection capacity, is the database starting to refuse no connections? Transaction throughput, has the rate of successful operations just dropped off a cliff? And of course, error rates, are you seeing a sudden spike in database errors?
Makes sense. Checking the database's own performance.
Then you need to look at the system level, the underlying infrastructure it runs on. CPU usage, memory usage, disk I/O, is it bottlenecked? Network latency and throughput between nodes. High resource utilization or network problems can often be early signs of impending database trouble.
Right, if the foundations are shaky.
The whole thing can crumble. It's like checking the vital signs of the patient, yes, but also the environment they're in. Is the room on fire?
Right. If the room is on fire, the patient's probably going to have a bad time eventually.
Exactly. And then there are replication-specific metrics. We talked about replication lag. That's a big one. Also, the rate at which the write-ahead log, the wall, that journal of changes, is being generated on the primary.
Why watch that?
Well, if wall generation suddenly halts, it could signal a really serious internal problem with the primary. You'd also monitor things like conflict resolution events happening on the replicas, if your setup allows for that.
Okay. Database, system, replication, anything else?
Yes, absolutely. Data consistency verification. This is super important. It might involve periodically running checks like comparing digital fingerprints, checksums on critical tables between the primary and replicas.
Just to be sure the data is identical.
Exactly. Making sure the data is actually the same. You'd also want to ensure the database schema, the underlying structure, hasn't somehow diverged between the instances.
Wow, okay. So it's a really in-depth, layered approach to spotting trouble brewing. The sources also mention a distributed monitoring architecture and consensus-based detection. Why are these important? Sounds like they help make sure we don't, jump the gun and failover unnecessarily.
That's exactly the point. A distributed monitoring architecture means your monitoring systems themselves aren't all sitting in the same potential failure zone.
Don't put all your monitoring eggs in one basket.
Precisely. You wouldn't want your monitoring system to go down at the same time as your primary database, right? That leaves you completely blind. Out-of-band monitoring is related. It means the monitoring infrastructure uses a completely separate network path from your main production data network.
Small. Keep it separate.
And having multiple perspectives on the health of the primary is also vital. You want probes checking from different network locations, maybe different cloud zones, or even regions. This helps avoid false positives.
Triggering a failover when there wasn't really a problem.
Exactly. That can be disruptive too. And consensus-based detection takes this a step further. It essentially requires agreement from multiple independent monitoring observers, maybe 3 out of 5 or something like that, confirming the primary is unhealthy before you initiate a failover.
Majority rules.
Yep. It dramatically reduces the risk of accidental, unnecessary, and often quite disruptive failovers. It's like needing multiple doctors to agree on a serious diagnosis before starting major surgery.
That's a really good analogy. You don't want one shaky sensor reading to trigger a massive response.
Okay, and what about synthetic transactions? That sounds like actively testing the water somehow.
That's a good way to put it. Synthetic transactions are essentially simulated user interactions with the database. You configure your monitoring system to regularly run these predefined test transactions, like pretending to be a user.
Exactly. Transactions that exercise the full range of database functions, reading data, writing data, updating data, you run these continuously. If these synthetic transactions start failing, even if the basic health checks like CPU or ping look okay, it's a strong indication that there's a real problem impacting functionality.
An end-to-end check. Very clever. Okay, so we've used our fancy monitoring. We've got consensus. We've detected a genuine failure. Now, who's the air traffic controller? Who actually makes the call to switch, decides which secondary becomes the new primary, and orchestrates the whole handover? That's where failover orchestration systems come into play, I assume.
Exactly right. These systems are the brains behind the automated operation. You typically have a dedicated failover manager. This could be custom software your team builds, or it could be specialized open source tools like Patroni for PostgreSQL, maybe Replication Manager for MySQL, or even the built-in failover groups offered by cloud providers.
So a dedicated coordinator.
Yes. And this manager relies heavily on a state store. This is a separate, highly available, and strongly consistent system. Think things like Etc., Console, or Zookeeper.
Why is that state store so important?
It acts as the definitive shared source of truth about the cluster status, who is the primary, which secondaries are healthy. It's absolutely critical for preventing those dangerous split brain scenarios.
Split brain. That still sounds like a nightmare scenario where, like, two databases both think they're the primary.
Exactly. That leads to data divergence, corruption.
Yeah.
It's bad news. The skate store helps prevent that by ensuring only one node can legitimately claim leadership based on the agreed-upon state.
Okay, we definitely need to dig more into preventing that. What about witness nodes? They sound like neutral observers in this drama.
They kind of are. In situations where you might have network problems, a network partition that could isolate the primary region from the secondary region, for instance, witness nodes, can help. You deploy them in a third, completely independent region or availability zone. They participate in the consensus process managed by the state store. Their vote helps the system reach a quorum, the minimum number of nodes needed to make a valid decision, like electing a new primary, even if some nodes are temporarily unreachable.
So they break the tie, essentially, during network weirdness.
Basically, yes.
Mm-hmm.
They help ensure decisions are made by a true majority, preventing a partition minority from making a wrong move.
Got it. And finally, the routing layer. How does that fit in?
The routing layer is what actually redirects the application traffic. Once a new primary is chosen, something needs to tell the applications where to send their connections. This could be global load balancers, database-aware proxies like ProxySQL or PG Bouncer, or maybe API gateways. They update their routing rules to point traffic away from the failed primary and towards the newly promoted one.
Like the final step in rerouting the planes to the new airport.
Exactly, closing the loop.
Okay, so the orchestration system, using the state store and maybe witnesses, makes the call to failover. But how does it ensure it picks the right secondary and promotes it in a safe, orderly way? That sounds like the decision logic implementation. There must be rules.
Oh, absolutely. It's a very carefully choreographed, multi-step process, not just a simple switch flip. First, there's usually multi-stage verification, meaning the system checks multiple times, maybe using different methods, to be really sure that the primary has genuinely failed and isn't just experiencing a temporary network blip or slowdown.
They'll be checking, triple checking.
Right. Then comes pre-promotion validation. Before a secondary is even considered for promotion, the failover manager needs to check its status. Is it healthy?
Right.
Crucially, has it fully caught up with replication from the old primary, or is it within the acceptable RPO limit?
Checking the lag again.
Yes. You wouldn't want to promote a secondary that's significantly behind and risk losing a bunch of recent committed data. That defeats the purpose.
Absolutely. Promoting a lagging secondary would be terrible. What's next?
Next is the promotion sequence itself. The specific set of steps taken to smoothly transition the chosen secondary into the primary role. This involves telling it to stop replicating, making it writable, updating the state store, etc. And this is where transaction boundary awareness is really crucial.
Transaction boundary awareness. Sounds technical.
It means the system tries, ideally, to perform the failover at a clean breakpoint in the sequence of database operations or transactions. This minimizes the risk of ending up with partially completed transactions causing data corruption or inconsistencies.
Make the cut at a safe point.
Exactly. And finally, once the new primary is supposedly up, there's post-promotion verification. The system runs checks to confirm that the newly promoted primary is actually functioning correctly, that it can accept right operations, that its health checks look good.
Confirming the new leader is ready for duty.
You got it, making sure the transition was truly successful.
Okay, fantastic. We've successfully failed over, in theory. But we haven't talked enough about that scary split brain scenario in detail yet. And just generally, how do we ensure we don't lose critical data during this whole potentially chaotic process? That must fall under consistency and data protection.
You're absolutely right. Split brain prevention is paramount. It's probably one of the trickiest parts of automated failover. Several mechanisms are used. Fencing mechanisms are key.
Fencing, like building a fence around the old primary.
Metaphorically, yes. It's about forcibly ensuring that the old, presumed failed primary can no longer write any data if it happens to come back online unexpectedly after a network partition heals, for example.
How do you fence it off?
It could involve things like network isolation, using firewall rules to block its database port, or running scripts that forcefully shut down the database service on the old primary, or even using storage-level locks that prevent the old primary server from accessing its data disks, basically stopping it from causing conflicting changes.
Pulling the plug, one way or another.
Pretty much. Then, as we discussed, quorum-based decisions via the state store and witness nodes are another critical defense. A majority must agree before a new primary is elected, preventing a partitioned minority from making a bad call.
Right. The majority rules principle again.
And another technique you sometimes see is a leader-lease system. The current primary is granted leadership status, but only for a limited time a lease. It has to periodically renew this lease with the state store. If it fails to renew it, perhaps because it's partitioned or truly down, it signals a potential problem, and it prevents a stale, isolated primary from continuing to think it's in charge indefinitely.
Time-limited leadership.
Clever.
Okay, those sound like really essential safeguards against chaos. What about protecting the integrity of the actual data itself during the failover? Preventing loss.
Right. Write-ahead log management is fundamental here, ensuring that all committed transactions are first hardened to the transaction log, the lol, and that log information is successfully shipped and applied to the chosen secondary before promotion happens is key. This greatly minimizes the risk of losing transactions that the application was told were successful.
So log shipping is critical.
Absolutely. Then there's conflict detection and resolution. If, despite all the fencing and quorum measures, writes did somehow occur on both the old and new primary during a network partition, which hopefully shouldn't happen, the system needs a way to detect these conflicts when connectivity is restored, and it needs a strategy for resolving them.
How do you resolve conflicts?
It varies. Sometimes it can be automated like last writer wins or based on predefined rules.
Right.
Other times, especially for complex conflicts, it might require manual intervention by a database administrator. Recovery point validation, as we mentioned, is about actively checking post-failover that your RPO objectives were actually met. Did you lose more data than your tolerance allows? And again, that transaction boundary awareness during the promotion process itself is crucial for maintaining data integrity at the point of cutover.
Wow. This is a level of intricate planning and defense in depth I never really considered. It's not just flipping a switch.
Not at all. It's layers upon layers of checks and balances.
Okay, so assuming the failover is successful, the new primary is up, fenced off the old one. How do our applications know where to connect now? That's where network and client connectivity comes in, right? Making sure there's a smooth transition for the users ultimately.
Exactly. A seamless experience for the applications and therefore the end users is the ultimate goal. Several techniques help here. Connection draining is often used during planned failovers. The system gracefully tells existing client connections to the old primary, hey, finish what you're doing, but don't start anything new, and disconnect soon. This gives applications a chance to finish their current work and then recommit cleanly to the new primary without abrupt errors.
A gentle nudge.
Kind of. Then connection pooling on the application side is also really important for rapid reconnection. Applications usually maintain a pool of ready-to-use database connections. When a connection breaks during failover, they can quickly grab a new one from the pool and hopefully connect to the new primary without much delay.
So the app needs to be smart about it too.
Definitely. Using read-write splitting can also help. If applications use separate connection strings or endpoints for read operations versus write operations, it can sometimes simplify the routing changes needed during failover, as only the write endpoint needs to change definitively. And of course, good retry logic built into the client libraries or application code is essential. If a connection attempt fails, maybe because DNS hasn't updated yet or the new primary is still stabilizing, the application should automatically wait a bit and try again, handling those brief transient hiccups during the switchover.
So the applications themselves really need to be designed with this potential handoff, this potential interruption in mind. What about the underlying network infrastructure? How does it know where to send the traffic globally?
Right, the global routing. Automated DNS updates are a very common and effective approach here.
Changing the address book entry.
Exactly. When a new primary is promoted, an automated process updates the domain name system, DNS, record the name the application connects to, like database.mycompany.com, to point to the new primary's IP address.
How fast does that happen?
Well, that depends partly on the time to live, or TTL, set on the DNS record. Managing that TTL carefully is important. Too long, and clients take ages to see the change. Too short, and you put extra load on DNS servers. It's another trade-off.
Always trade-off.
Always. For more advanced routing, you might use global traffic directors. These are services offered by cloud providers like Azure Traffic Manager, AWS Route 53, Application Recovery Controller, or Global Accelerator. They can do more sophisticated health checks and latency-based routing to direct traffic globally.
More intelligent routing.
Yes. And finally, integrating with service discovery systems like Consul or Eureka is another option. Applications can query these systems directly to dynamically find the current location of the primary database service, sometimes bypassing DNS altogether for internal connections.
Lots of options for finding the new primary. Okay. This all sounds incredibly complex, but also incredibly well thought out when done right. But how do we actually know if all this intricate machinery works when a real disaster strikes? Wishing and hoping isn't enough, right? That's where having a robust, comprehensive testing strategy must be absolutely critical.
Oh, 100% critical. Absolutely non-negotiable. Theory is one thing, but proving it works under pressure repeatedly is everything.
So what does good testing look like?
Regular failover drills are the starting point. And I mean regular. Ideally, these should be conducted maybe monthly or at least quarterly, and crucially, in environments that closely mimic your actual production setup. You have to practice.
Find the kinks before a real event.
Exactly. Then there's chaos engineering. This is more proactive. You intentionally but consolably inject random failures into your system, simulate a network partition, kill a database process, overload a server.
Injecting random failures into a production-like system still sounds bold.
It can be nerve-wracking the first few times, but the goal is to validate that your automated recovery mechanisms kick in exactly as you expect them to automatically. The insights you gain are invaluable for building real confidence and resilience.
I believe it. What else?
Performance validation is also crucial. You need to measure the impact of a failover on your application's performance. How long does the blip last? What's the performance like after the failover is complete? Does the new primary handle the load okay?
Measuring the impact.
And rigorously tracking your recovery time objective, or RTO. That's the total time it takes from failure detection to full service restoration. Tracking that RTO against your defined business goals during these tests is vital. Are you meeting your targets?
RPO for data loss, RTO for downtime. Got it.
Right. And the sources also highlight the importance of scenario-based testing. It's not enough to just test one generic primary fails scenario.
You need to test different kinds of failure.
Exactly. You need to test a whole range of different plausible scenarios, like planned maintenance failovers. These should be smooth, orderly, zero data loss, minimal downtime. Test that process.
Okay.
Then, disaster recovery testing. This involves simulating a complete regional outage. Does your cross-region failover strategy actually work end-to-end as intended? Can you run your business from the failover region?
The big one.
Yep. Network partition simulations are critical for really hammering on those split-brain prevention mechanisms we talked about. Do the fencing and quorum rules work correctly when parts of the system can't talk to each other?
Stress testing the safety nets.
Exactly. And testing for cascading failures. This is where one initial, maybe small problem triggers a chain reaction of other failures down the line. Identifying those potential weak links through testing is crucial.
Wow. Okay, that's comprehensive testing. Finally then, how do you actually manage and monitor all of this in the real world, day in and day out, making sure it stays working, stays healthy? That's where operational integration comes into play, right? Making sure this isn't just a project you set up once and forget about.
Absolutely. Good engineering is only half the battle. Effective ongoing operations are just as important. And this relies heavily on observability and alerting.
Seeing what's happening.
Right. A unified dashboard is pretty much essential, something that gives your operations team a clear, consolidated, real-time view of replication status, lag metrics, system health, failover status across all your regions, all in one place.
Mission Control Center.
Kind of, yeah. An event timeline is also incredibly valuable. This should provide detailed logging of all failover-related events, detection, decision, promotion steps, verification, DNS updates, along with correlation IDs, so you can easily track a single failover event across all the different systems involved. Indispensable for troubleshooting when things don't go perfectly.
Seeing this sequence of events.
Yes, and the automated generation of postmortem analysis reports after any failover event, whether it was planned or unplanned, is really key for learning. The system should gather the relevant logs, metrics, and event data automatically to help the team understand exactly what happened, why, and identify any areas for improvement.
Learning from every event. Smart. So it's not just about the technology working flawlessly every time, but also about having the tools to understand what happened, especially if it wasn't flawless, and how to make it even better next time.
Precisely. Continuous improvement is the name of the game.
What about ongoing automation beyond just the failover event itself? Self-healing capabilities.
Yeah, automation and self-healing are really important for long-term operational efficiency and reducing manual toil. This includes things like the automated re-replication setup. After a failover, the new primary needs to start replicating its changes to the other secondary regions, including potentially the old primary once it's recovered.
Hmm.
Automating that setup is crucial.
Getting the replication flowing again automatically.
Right. Also, dynamic scaling might be needed. If the node that got promoted was previously just a read-only replica, it might need more CPU, memory, or IOPS to handle the full production write workload. Automating that scaling based on load can prevent performance issues
Adjusting resources on the fly.
and potentially running background reconciliation processes. These could be jobs that periodically compare data between the primary and secondaries, looking for and potentially automatically fixing any minor data inconsistencies that might have crept in during a failure event, maybe due to that replication lag we discussed.
Constant vigilance.
Essentially, yes, keeping the system healthy and consistent over the long term.
Wow. This has been an incredibly detailed and frankly sophisticated look at what goes into automated database failover in a multi-region setup.
Right.
It's clearly far, far more involved and requires significantly more forethought than I think most of us probably ever realize when we just use a website.
Indeed. It really highlights that building a truly resilient, highly available system isn't about one single piece of technology. It requires meticulous planning and integration across architecture, the replication itself, comprehensive monitoring, smart orchestration, rigorous testing, and ongoing operational discipline.
Well, for you, our listener, I really hope this deep dive has illuminated the immense effort and complexity happening behind the scenes. All this work to ensure that the applications you rely on every single day remain highly available and that your data stays safe, even when major disruptions inevitably occur.
Yeah, it really underscores the complexity and honestly the ingenuity that underpins so much of the reliable internet experience we often take for granted.
That certainly does.
And maybe it leaves you to consider this. Given this incredible level of engineered, automated resilience we've just spent time unpacking, what are the broader implications? What does this mean for our expectations of online services in the future?
Good question.
We've become very accustomed to seamless, always-on experiences, but as you now have a better sense, there's this vast, intricate world of engineering making that possible. It's maybe worth pondering the constant trade-offs being made between this level of complexity we've discussed and the ever-increasing reliability we demand. And maybe think about what other unseen layers of automation and resilience might be quietly working right now to support the digital world all around you.